Okay, in this section, we're going to introduce vectors. A lot of you probably had vectors before, but can't assume everyone has. A vector is used to represent any quantity that has both magnitude and direction. The magnitude and direction, for example, the position or the velocity, forces a lot of times in physics are represented by vectors. You can form a vector if you have two points. Suppose we want to form the position vector from the point -2, 1 to the point 4, 3. So what you do to form a vector is you just subtract the x coordinates and subtract the y coordinates. Technically, the vector 6, 2 is different than the point 6, 6, 2. You could say this vector right here, let's call it A. You can actually put this wherever you want. That's a really important thing about vectors. You can move them around. So if you take this and put this in what's called standard position with the initial point at 0, 0, then this is a vector 6, 6, 2. The terminal point of the vector would be the point 6, 6, 2. Okay? But the vector and the point are not the exact same thing. The one thing difference is that the vector can be moved around, but the point can't. Anyway, so that's how you form a vector from points. Okay, now like I said, this is one of the key things about vectors. Vectors can be moved, and oftentimes they are, especially when you do things like add vectors. As long as you don't change their length, which is called the magnitude, and the direction, as long as you don't change those things, you can move them around. You can take a vector and you could multiply it by a real number. Real numbers we're going to call scalars. Okay, so when you see the word scalar, it just means by a real number. The way you define scalar multiplication is when you multiply a vector. By the way, vectors always have hats on them or something. Either they're bolded or they have an arrow or something to signify the difference between vectors and real numbers. When you multiply a real number times a vector, you multiply each coordinate. That makes sense. So what would 1/2 a be? If a was the vector, remember what a was? A was the vector 6, 2, so 1/2 of a is written like this, and it becomes the vector 3, 1. The significance of that is that it's a shrink. You're shrinking the length of a. You don't change the direction, but whenever you multiply a vector times a scalar, you're either making it longer or shorter. And if you multiply by a negative number, it actually causes a reflection as well. It goes in the opposite direction. Anyway, so how do you find the magnitude of a vector? Well, you can kind of see this. It's the Pythagorean theorem, basically. The magnitude of a vector, it's the square root of the x coordinate squared plus the y coordinate squared. So the magnitude of vector A would be the square root of 6 squared plus 2 squared, which becomes the square root of 40, which is 2 radical 10. So that would be the length of this vector. Now with vector addition, if you have two vectors, you can add them. The way you add vectors together is just to add the coordinates. So suppose A is the vector -1, 3, and B is the vector 2, 1. Then the vector A plus B, you add the coordinates, you get the vector 1, 4. So here's the way to interpret that. When you add the vectors and you get the vector 1, 1, 4, you literally move, when you're adding A to B, you're taking the vector B, and since you can move it, we're going to move it up here. As long as you keep it the same direction, that this vector has the same length and direction as this one. And then you form this new vector, vector AB. I should say the vector A plus B is this vector in standard position that it starts at 0, 0 and ends at the tip of vector B. And guess what? This vector A plus B turns out to have the coordinates 1, 4. So this is how you would interpret the addition. And the magnitude of this new vector, A plus B, is going to be the square root of 1 squared plus 4 squared, which is the square root of 17. Now, the direction or the angle between A plus B and the positive x-axis, if you think about this vector here, that's right here. This is A plus B, this vector. if you look at the components, the x coordinate's 1, the y coordinate's 4. So using trig, the tangent of this thing, this is your angle theta, right? The tangent of theta would be this 4 over 1. So theta would be the inverse tangent of 4. That would be the direction or the angle between a plus b and the positive x-axis. Now, how would you interpret a minus b? It's similar. A minus b would be a plus negative b. So what you'd have to do there is this. Well, first of all, it's equal to a plus negative 1 times b. So you should get this vector. But the geometric interpretation is you would take b, you'd multiply by negative 1, and then you would move negative b over to the tip of a. This is negative b. And you form this new vector from the 0 to the tip. This would be a minus b, would be this vector right here. Notice the coordinates of that, the terminal point of that vector is negative 3, 2. So there is an interesting geometric interpretation of addition and subtraction. Let's see what else. Some special vectors. These are oftentimes called the base vectors in R2, I and j. I is just the vector 1, 0, and j is the vector 0, 1. You could think of I as this vector of unit 1 in the horizontal direction, and j is the vector with length 1 in the vertical direction. The significance is that any vector can be written in terms of them. We say any vector can be written as a linear combination of these two vectors. You see, AB couldn't be written as a times the vector 1, 0 plus b times the vector 0, 1. But isn't that just I and isn't that just j? So, and in fact, we do use this notation quite often, the I and j notation. Sometimes it's easier, sometimes it's not. Let's see. The question is, suppose a vector has magnitude 4 and the angle between v and the positive x-axis is negative pi over 6. The first thing I want you to do is how would you find the components of the vector v and express using I and j notation? Well, if you look at the picture here, looks like this. The length of this vector is 4, and this is your angle. So if you look at the components, isn't the x component of this vector v sub x? Wouldn't that be the magnitude of v times the cosine of theta? And wouldn't the y component of v be the magnitude of v times sine of theta? That's how you could do it. So you'd get 4 times cosine negative pi over 6, which gives you 2 radical 3. And the y component would be 4 times the sine of negative pi over 6, which gives you negative 2. So the components are 2 radical 3 and negative 2, but I didn't answer the question. I was supposed to answer it in terms of I and j, so it'd be 2 radical 3i minus 2j. That's how you'd write it in terms of I and j. How about this? Find a unit vector in the direction of v. Well, we're going to do that a lot, so you got to be able to do that. How do you turn a vector into a unit vector? What you would do is divide by its magnitude. So you'd first find the magnitude. Well, that was actually given. The magnitude of v was 4. So if you take when you multiply by 1/4, it's the same thing as dividing by 4, right? So when you divide each component by 4, you end up with radical 3 over 2 negative 1/2. That would be the unit vector in the same direction as v. It would look kind of like this. If this is vector v, the vector u, the unit vector would look kind of like that, right? It would have the same direction, but the magnitude would be 1. Okay, a couple more things. So moving over to R3, the set of all vectors in R3 is actually called V3. So they're different. R3 is a set of all points in 3 dimensions. V3 is a set of all vectors in 3 dimensions. It turns out instead of I and j, we have I, j, and k. Think of I as the vector along the x-axis that has length 1, j is the vector along the y-axis that has length 1, and k is the vector along the z-axis that has length 1. And sure enough, every vector in V3 can be represented in terms of I, j, and k, like we did before. All right, suppose we have 2 vectors. This is your vector 1 in R3, in V3, I should say. This is your vector b in V3. So A might look like this. To think of A, you would go 2 in the x, 6 in the y, and 3 in the z. So I'm putting it in standard position. So this would be the vector A. What is the magnitude of A? Well, the magnitude of A, you would just, same definition, you would take the square root of the sum of the squares of the components. So it'd be the square root of 2 squared plus 6 squared plus 3 squared, and you get 7. So the length of this vector here is 7 units. How would you find the unit vector in the direction of A? Just like we did before, you would have to divide each component of A by 7, right? So you'd get 2 over 7, 6 over 7, and 3 over 7 would be the unit vector in the direction of A. And you could find, you could do vector addition like this. You could take 3 times A and subtract 2 times B. You would just take the A vector, multiply by 3, take the V vector, multiply by -2, and add the components. You get 0, 6, 13. All right, that's it. We'll see you next time. Bye-bye.